Hey, welcome back. So we have a brand new section here on a brand new, exciting, hopefully exciting, data structure, trees. So trees, aside from being everyone's favorite perennial plant, are also a classic data structure. They're taught in computer science classes around the world. They're also very commonly used all around the world. So they are a bit of a step up from linked lists, a little more complicated, but also maybe a little more interesting. So quickly, let's run through our objectives. We want to define what a tree is, compare and contrast trees with linked lists and arrays and things like that. Explain the differences between, there's different types of trees that we're going to talk about. Just plain old trees, then binary trees, and then finally binary search trees. And binary search trees is what this section is really focused on. But we're going to talk about these three categories. And then most of what we'll be doing is implementing a bunch of operations on binary search trees. So we'll define our own BST, binary search tree. I'm just going to say BST from here on out. Our own BST class and add a bunch of methods like we did with a singly linked list or a doubly linked list. But first, we have to talk about what a tree is. So trees are data structures that consist of nodes, just like a linked list did, but they are in a parent-child relationship, hopefully consensual. We basically end up with branches. So from one node, we can have it connect to one other node, or 2 or 3 or 10 or 0 nodes. But we end up with these branching structures, hence the name tree. Think of an actual tree. We follow a branch and it splits at some point, and then that branch can split and they can keep splitting, and we end up with all these different little branches off of this main original branch. Now often when we see diagrams, they look more like this, where they're top down rather than a tree which grows from the ground up. It doesn't matter, right? It's the same exact structure, it's just flipped. But usually we'll see them represented like this. So here is an example of a tree. Each one of these circles represents a node, just like it did on our linked list. But notice this is very different than a linked list in that each node can point to more than one, or can have more than one reference to another node. So this is our topmost node. We'll go over the terminology, but this is called the root, and it points to 9 as another node. It also references 12 and 8 and 99 and 10. And each of those nodes potentially references one or more other nodes, or actually 0 in this case. This is a dead end. Nothing comes after. 12 has 1, 2, 3 children. 99 has 2 children. 10 has 2 children, and so on. So this is an example of a tree, but they're not always like this. We might have a tree that looks like this. We have a single topmost node, and it branches off into 2 nodes. And then each of those only branches off into 1 node. So it doesn't have to be this nasty, complicated mess. It can be simple. This is also another example of a tree. And, it doesn't have to be numbers. We can, just like a linked list, we can store data in there. We can store strings, or, if you wanted to, you could store anything, arrays, or I don't know. What would you want to put there? Most of the time it's numbers and strings, but it could be anything. So when we talk about lists are linear. It's one thing, and then the next, then the next, then the next, then the next. Everything is in a line, in a row. Trees are non-linear. They can branch. We can have more than one pathway through a tree. With a linked list, there's one path. In a doubly linked list, you could work backwards or forwards, but still there's one line through our data structure. In trees, there's many different paths we could take. Just like the journey of life, right? You end up here, if this is a decision you have to make, you could make one choice and go this way. And if you do make that choice, you'll never know what was over here. And then you make another choice, right? This is one path here. This is another path. This is another path. With a linked list, there's only one pathway through. So you can think of a singly linked list as a very special case of a tree. So this could be a tree. It's not a great use for a tree, but if we had this 2 pointing to 12, which points to its child 11, you could represent that as a linked list, 2 to 12 to 11. But you probably wouldn't do that. You would probably just use a linked list if this is what your data looked like. But I just wanted to show that this is a special case. But as soon as we added a second branch here or here, it's not a linked list as soon as it becomes non-linear. Now, when we're talking about trees, there are some rules. So this is not a tree. So what we have here are nodes that are referencing other nodes that are not below them, if that makes sense. They're not children. So a node can only point to a child. It's a parent-child relationship. We can't have a child pointing to a parent. We can't have a node pointing to a sibling. We can't have what's going on here. This is actually what's known as a graph. We'll talk about these later. A tree, every node is moving away from the root node, if that makes sense. All these arrows have to point down if we were trying to represent it. So this is also not a tree. It looks like it could be because all the nodes are pointing away from the root, but there is no one root. We have two beginnings of this tree. So that's not a tree. We need to have one entry point. So as I mentioned, there is some terminology. The root is the top node in a tree. So if we go back to this tree, this is the root. A child is a node directly connected to another node when moving away from the root. A parent, it's the converse notion of a child. I think those two make sense. Siblings are nodes that have the same parent. A leaf is a node with no children on this tree. This is a leaf. It has no children. It's also a child of this node. This is the parent of this node. This is the root. And lastly, there's terminology for the connection, which we call an edge. It's the actual arrow between one node and another, or at least in my diagrams, it's an arrow. Okay, so we have root. This is an edge. This is a child relative to this parent, but it's a parent relative to this child. This is also a leaf. It has no children. And I think that's all the terminology, right? Edge. Yeah, I covered it all. Okay, so that's basic terminology. It's just helpful for us to discuss when we're implementing code. I'll say something like, all right, we need to, add the edge from this parent to this child. Or I might say, let's check if a node is the root or if it's a leaf and so on. Okay, so we'll leave off here. Next, I'm going to talk about some real applications of trees, and we'll also introduce binary trees and binary search trees in the next video.